All right, so we're going to enter what's called molecular geometry. Basically, how do atoms that are sharing electrons with other atoms, how do they configure themselves around what we call a central atom? All right, so let's just look at it. I've got a carbon. That carbon right there, we've got 4 valence electrons. 1, 2, 3, 4 valence electrons. And now that we have 4 valence electrons, we're going to have ourselves, let's say, 4 hydrogens. 1, 2, 3, 4 hydrogens. Each one of those is 1 valence electron. 1, 2, 3, 4. Now, what's going to happen is each one of those hydrogens can share an electron with a carbon, and each carbon can share an electron with a hydrogen. And so we create ourselves a bond, a bond, a bond, and a bond. But what's going to end up happening is this is a 2D world. So just as it sits on the board, we have a 2D model going on here. We want to find out what this thing looks like, how it exists in the real world. We've talked about this already. We've done this already in chemistry. We talked about the idea. Give me a second. We talked about the idea that all of these atoms want to stay away from each other as far as possible if they're negative charges. So all negative charges repulse. And so if we look at this model right here, we have 1, 2, 3, 4 things around that central atom right there. So with 4 things around that central atom, you start seeing a different shape here. It's not just a cross. It's not just 4 things sitting like this. There are 4 things sitting like this. And what this is, it's called a tetrahedron. And so we look at that shape right there, and we can see it's like a little 4-sided pyramid. 1, 2, 3, bottom 4, a 4-sided pyramid. And so that's tetra meaning 4, hedron, which is like a shape. So this is a tetrahedron, 4-sided pyramid. Now, why? Why do we have to have a shape like that? Why is this not okay? Well, that brings us to what we call VSEPR. Always mispronounced. Always sounds like you're spelling the word VES, but it's VSEPR. This is the valence shell electron pair repulsion theory. Valence shell, outermost electrons being shared, outermost electrons. Valence shell electrons are negatively charged. Pairs, there's pairs of them. And they might be shared, or they might be what we call a lone pair. So they're not being shared, but there's still a pair of them there. Remember, every orbital has 2 electrons. Repulsion. Remember electrostatic repulsions. Like charges repel. Opposite charges attract, like charges repel. And so the goal, once again, I've said this 42 times already, the goal is to create as much attractions as possible, maximize attractions, but we want to minimize repulsions. We want to minimize that negative to negative push away. And so this right here, for 4 things around the central atom, this is a 90-degree bond angle. This is a 90-degree bond angle, 90-degree bond angle, 90-degree bond angle. Okay, decent sized bond angle. But that negative to negative charge, in fact, the negatives are here, these negative to negative repulsions, they're going to push. They're going to push away. In a 2D world, okay, that'd be as far as we can get. But in a 3D world, a world we actually live in, we're going to put it like this. We're going to have them farther away from each other. And why is that? Why in the world would that be? Because this is a 109.5 degree bond angle. 109.5 degree bond angle. And so you can see, if you look, That is not a right angle anymore. That is not a 90-degree angle. That's a 109. And what does that mean? The more distance there is between these electrons, the less repulsions they're going to be. And the more stable, the more chill these atoms are going to be, the more likely they're going to be that way. Because once again, all of these things are just going by the simple principle of like charges repel, opposite charges attract. And so we are minimizing those repulsive forces. And so they're sitting like that. So this right here, in a Lewis structure, yes, we would draw it as a carbon, hydrogen, 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 hydrogen. This would be a Lewis structure of carbon. And then just the reader, the writer, the chemistry person has got to know when they look at that, that the reality is that this and this is the same thing. And in fact, if you want to draw it geometrically, you could say that you have a carbon, you have a hydrogen going up in the air, you have a hydrogen coming out to the side, and then you have a hydrogen disappearing into the distance. A little dotted line like that. I don't know if you guys can see that. A dotted line like that. That's disappearing into the distance. And then we would have one coming out at you. And so that line right there, when we draw it like that, it's basically longitudinal perspective. Like if you look down a railroad track, you can see that the railroad looks like it's closer together when it's close to you, or look at a room, the farther the thing is away, the more it's gonna feel like it goes to a single point. And so it's just kind of a geometric way of doing it. You might not ever have to really draw it like this, but this and this are the same thing. This is just a Lewis structure. This is kind of drawing it geometrically. And what we would say is this is a tetrahedron. That's a tetrahedron with 109.5 degree bond angles around the central atom. So this carbon would be the central atom there. Other than that, there's other things to talk about. We'll talk about hybridization, polarities, and stuff like that, but that's how this thing's gonna work.